Hello, everybody, and welcome to our last chapter of the year. This is chapter 9, stoichiometry. We're going to go through the first two sections of chapter 9, section 9.1 and 9.2, and we're going to go through and do some ideal stoichiometry problems, okay? So this kind of is the culmination of everything we've done thus far with being able to write a formula, being able to balance that formula, and then finally being able to do a little bit of the mathematics of using these chemical equations. So you can see here on the screen, stoichiometry is the branch of chemistry that deals with the mass relationships between reactants and products in a chemical reaction. So we're going to look at, if you react so much of this with so much of this, how much of this is going to be produced. You can see there the other bullet point, stoichiometry comes from the Greek word stoichion, meaning element, and metron, meaning to measure. So you'll be measuring the elements. Okay. And everything in stoichiometry is based off of the balanced equation. You cannot do stoichiometry without a balanced equation. So what you just did in chapter 8 with writing that balanced equation, we'll base all of our calculations off of that. Okay. So this first section is just a real quick introduction, and really what we get out of this section is what is a mole ratio, okay? And it just comes, like I said, from the balanced equation. So we're going to be doing reaction stoichiometry, and you can see there reaction stoichiometry based on the chemical equation and the law of conservation of mass. So that's just saying, making sure that the reaction is balanced, okay? All stoichiometry calculations start with a balanced chemical equation. This equation gives the relative number of moles of reactants and products. Okay, so the mole ratio, in any stoichiometry problem, you're going to have this step. Okay, you may have other steps that we're going to add later, but the basic step in stoichiometry is the mole ratio. So it's a conversion factor that relates the number of moles of any two substances in a chemical reaction. So really what you're doing with the mole ratio, instead of canceling out a unit, is you are canceling out a substance. You're going from one substance to the other. The mole ratio can be obtained from the balanced equation, and the coefficients represent the relative numbers of moles. So if we look at, here's our coefficients. We have a 2, we have a 4, and we have a 3. Okay, and these are relative mole amounts. So really, we could say for every 2 moles of Al2O3 that decompose or break down, you produce 4 moles of Al and 3 moles of O2. So that's really the mole ratio. If we're looking at a ratio for every 2 moles, okay, of Al2O3 that you have, well, that's a bad straight line. Sorry. You get 4 moles of Al. Okay. So that's a ratio that reflects the amounts of Al2O3 to Al. You could do Al to Al2O3. You could have for 4 moles of Al, you get 2 moles of Al2O3. You can do both products. So here's another mole ratio. For every 4 moles of Al, you get 3 moles of O2. Okay, so there's another mole ratio. You could do O2 to Al2O3. And really what you have here, you can see these are going to fit into our factor labeling problems or dimensional analysis. You're going to cancel out the actual substance. The unit's the same. It actually cancels out when you divide a mole by a mole. But what you're going to change here is the substance. Okay? So that sort of takes us to section 9.2 with these ideal stoichiometric calculations. And the first type we're going to do, and your type for today, is mole to mole, these mole to mole calculations. So we're just going to go from moles of substance A to moles of substance B. This could be reactant, This could be product. This could be product to product. It could be reactant to reactant, whatever two substances in the chemical equation you are relating. Note that you're not changing the unit. You're starting with moles and ending with moles. The only thing you're changing is the substance from substance A to substance B. And you're going to use the mole ratio from the balanced equation to do that. Okay, so this first question here, this isn't on your note guide. Okay, you can just kind of follow along, and then we're going to do 2 examples to wrap up. Okay, so the mole ratio can be used to calculate the moles of one chemical from a given amount of a different chemical. So here's an example problem. So how many moles of chlorine are needed to react with 5 moles of sodium to form sodium chloride? So here's the balanced equation from that. Sometimes you have to write these. For us this year, I'll be giving you the balanced equation. Okay, that's sort of what we did last chapter with balancing those. So just to kind of get you moving forward, you'll be given the balanced equations. Okay. Sometimes maybe for a homework or something, you have to write it, but I'll give you those for like an exam or something like that. Okay, so we have 5 moles of sodium. That's right here. We have 5 moles of this, and we want to know how many moles of this chlorine are you going to need to use to form sodium chloride. Okay, so I'm going a little fast there. Okay, so here's your setup. For every 5 moles of Na. So this you actually had right here, and this should actually say 5.0 moles of Na, just for our significant figures. Now, where did this come from? Okay, these right here. They came from the balanced equation. So you can see those arrows. For every 2 moles of Na, it went on the bottom so Na can cancel. Okay, you actually want to cancel out moles of Na with moles of Na. For every 1 mole of Cl2, that goes up top. That's what we want in our answer. Remember, if there is no coefficient there, it's just a 1. So you write down your 1 there. Okay, and then you just do the math. 5 times 1 divided by 2, and you get your 2.5 moles of Cl2. It's as easy as that. It's just one step, going from moles of one substance to moles of another. You use your mole ratio from the balanced equation, and it's simple math. It's just whole numbers. Okay, so here's our first example problem. How many moles of lithium hydroxide are required to react with 5.00 moles of carbon dioxide? So we have 5.00 moles of this based on this balanced equation, and we want to know how many moles of this are we going to need. Okay, and you can see that some of these mole ratios, for every 1 mole of this, you need 2 of these. So you need double the amount of this to react with this. But let's set it up correctly. So we have 5.00. Close that up right there. Moles of CO2. Okay. Now here's where our balanced equation is. For every 1 mole of this, and that's a 1, you don't have to write that in there, but for every 1 mole, that goes on the bottom because we want it to cancel, of CO2. Okay, then we have this right here. We have 2 moles of LiOH. 2 moles of LiOH. Okay, moles of CO2 cancel, moles of CO2 cancel. 5.00 times 2 divided by 1 is 10.0 moles of LiOH. That's a bad H, but it's fine. Okay, that's it. Okay, that's a mole calculation. For any stoichiometry, you are going to, it's 8 o'clock, I gotta check in. You use that mole ratio stuff. Okay, so last one, here we go. Ammonia is widely used as a fertilizer in many household cleaners. How many moles of ammonia are produced when 6 moles of hydrogen react with an excess of nitrogen gas? Now, when you see that, that just means that you have plenty. Okay, you have so much where that you have enough N2 where when the H2 runs out, the reaction is going to stop. Okay, so don't worry too much about that. So we have 6 moles of this. Okay, remember, you can always find the substance in the balanced equation. You have to. So hydrogen gas, that's this. They're talking about this right here. So we want to know how many moles of ammonia. And this is ammonia right here, if you didn't know. And if you weren't sure, this is hydrogen, this is nitrogen. There's only one thing left. That has to be the ammonia. Okay, so we have 6 moles of H2. Okay, there we go there. Okay, now here's our equation. Look it up for our mole ratio. For every 3 moles of H2, that's going to be here. Oops, this is H2. H2, there we get 2 moles of ammonia. So 2 moles of NH3. Okay, moles of H2 cancel, moles of H2 cancel. So we go 6 times 2, that's 12. Divided by 3, that's 4. So we get 4.00 moles of NH3. Okay, that's it, 4 moles of NH3. So this is the beginning of, like I said, stoichiometry. Every stoichiometry problem will have this. We're eventually going to go from changing moles to grams, but you've done that before. You did that chapter 3, you did that chapter 7, and adding that. But what we add from now on isn't going to be anything that you haven't done already. Okay, so for today, there's a little homework assignment with multiple calculations. Make sure you do those. Check your work with the provided answer key, and then mark the assessment that you have completed the assignment. Okay, see you guys later.